Hi everyone, this is Maria, and this is an introduction to the periodic table. I'm also going to be talking about the octet rule today as well. Alright, so the goals of this video are really to talk about the different families on the periodic table and their properties, and to talk to you about how the octet rule influences the organization of the periodic table, and in fact, of course, what the octet rule actually is. So we're going to start with the broadest categories, so metals, nonmetals, and metalloids. You can see pretty much immediately that metals are the majority of the periodic table by far. People often don't think of things like magnesium and calcium and sodium as metals, but they are classified as metals. We'll talk about some of the properties, but in fact all of those elements by themselves have those properties. Then there's the nonmetals, a much smaller portion of the periodic table, but very important. It actually contains some of the most important elements for life. Carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, and hydrogen, all of those incredibly important. So we'll definitely be talking about those a lot as well. Metalloids are a little funny. You'll see that they're in fact just pretty much right in the middle of metals and nonmetals. And they in fact actually have similar properties to some metals and similar properties to some nonmetals, and so it's sort of like a mix. That's sort of like why we call it a metalloid itself. It's really a mix of metal properties and non-metal properties. So speaking of those metal properties, you can see in the table on the right, metals tend to be shiny, solid at room temperature, except for our good friend mercury, good old Hg, and they're good conductors of both heat and electricity. Non-metals, on the other hand, they're dull. They could be a solid, a liquid, or a gas at room temperature, and they're not good at conducting either heat or electricity. So just be aware of that. All right, so let's get into it and start talking more about those more specific categories. So there's the alkali metals on the very left. They're incredibly reactive. They're really cool to see. You're going to really have fun seeing the demonstrations that we all end up doing. And that's honestly all I want you to kind of know about it. It's a reactive metal. Then alkaline earth metals, all I want you to know about that for right now is that it's a reactive metal, but it's not as reactive as the alkali metals. Just keep that in your mind for right now. All right, the transition metals. Some of my favorite elements are in here. They are not very reactive at all. You'll see this when we test it, all that sort of stuff. But just keep that in your mind for right now. The cool thing about transition metals that I really like is that when they're in compounds, they often form very beautiful, colorful compounds. So if you remember copper, copper is a transition metal. And since copper is a transition metal, if you remember the color of the solution that you used for the flame test, well, that solution was this pretty blue color. So just kind of cool to think about. Halogens. I'm skipping right along. There's a reason why I boxed off those four. At at the end is one of those ones that people tend to argue whether it's truly a halogen or not a halogen, and so that's why I boxed at least fluorine, chlorine, and bromine, and iodine. They're all ones that are definitely halogens. The other thing to be aware of for the halogens is that they're very reactive, incredibly reactive, but they are non-metals. So just keep that in mind for right now. And then, of course, I'm going to talk about the noble gases. The noble gases are very interesting because they don't react whatsoever. Keep that in your brain bucket for later. The other thing to know about noble gases is that noble gases were actually not discovered around the time of Mendeleev. So actually, when he made his periodic table, he didn't make them with the noble gases. It's kind of interesting to think of. All right, the rare earth metals, there's the lanthanides and the actinides. The actinides are really cool because they end up having radioactive material, or radioactive elements are found in the actinides. And then the lanthanides are interesting, but not, but basically because of the fact that they all end up having the same charge as an ion. Kind of cool. All right, so let's think about why it's organized this way. Well, when you did the card sort activity for chemistry this last week, you ended up organizing it, and often what you did was you saw those dots on the card and you were like, I'm going to organize it according to those dots. Well, you organized it the way that the periodic table is actually organized. That's one of the ways that it is in fact organized. There's other ways that it's organized as well, but that's probably the most important. So kudos to all of you for picking up on that. So As I said, though, if we're talking about those electrons, we should maybe talk about them a little bit more. So this comes back to talking about electrons and talking about the octet rule specifically. So the octet rule is really just saying atoms will gain or lose valence electrons to achieve a filled outer energy level to become stable. So essentially, once you have that filled outer energy level, you're really, really stable. Valence electrons, that's not a term we've used before. They're honestly the most outer electrons in an atom. You'll kind of see that more just from the pictures that I'm showing you, and we'll talk about this as we're going through as well. So if I'm talking about energy levels, there's more and more as you go down the periodic table, and you can use what's often referred to as the 288 rule for the first 3 rows. So I'm going to talk about that using the picture right over here. So if you look at hydrogen and helium, well, hydrogen is pretty darn reactive, but helium is not. The reason why? Well, helium has that filled outer energy level. It doesn't need another electron. It doesn't need to lose an electron, nothing like that. Hydrogen, on the other hand, hydrogen definitely wants either another electron or it's actually okay with losing it. That's an interesting thing to talk about, and you'll talk about that in class as well. It's maybe a little easier to maybe see that for the next row. So you can see that lithium's first energy level is completely filled, but it only has 1 electron in its outer level. So wouldn't lithium just be much happier if it lost that outer electron? Yeah, in fact it would. It would have the same amount of electrons as helium. And helium, we know, is a noble gas. And noble gases are stable and very non-reactive. What about beryllium? Okay, so if we're looking at beryllium, there's 2 in the outermost level and 2 in the inner. Okay, same sort of thing. It would be pretty easy to lose those 2 electrons. Let's skip ahead a little bit. What if I'm talking about something like oxygen? So you can see that there were 2 on the inner one and 6 in the outer one. Okay, cool. So wouldn't oxygen be really close to neon's configuration at the end over there? And neon's configuration, well, it has a completely filled outer shell. It has 8 in its outer shell. So oxygen just needs 2 more electrons to be completely full. Fluorine needs 1 more electron to be completely full. When we're talking about this rule, I will tell you this. It really only works for the first 3 rows in the periodic table. So just keep that in mind. You can use it a little bit further, but I will tell you when we're talking about the transition metals, you can't predict those charges very easily. Again, we'll talk about that more later. So let's talk about how this really allows us to predict the charge of an ion. So you can see that everything that's in that very first column, so the alkali metals plus hydrogen, both of those end up with a +1 charge. Then our alkaline earth metals, they all have a +2 charge. The +3 is a little tricky. Boron's not amazing at being a +3, so I would skip over boron. But aluminum and gallium, those are both +3 charges. You'll notice that in the middle there's some transition metals that have the same charge every single time. You're going to learn about those more later, and I'm going to have you make sure that you, in fact, have to memorize those 3. But don't worry about it for right now. We'll talk about it more later. So skipping on over to nitrogen, you see that now we end up with negative charges. You see that for the nitrogen column, for the oxygen column, and then when we get to fluorine, the halogens column. And then the noble gases, this should make sense to you, it doesn't like to ionize. It doesn't want to lose an electron. It doesn't want to gain an electron. It's going to have a charge of 0. So what we know about those periodic table trends is really, really helpful. And let's see if we can practice this. So I'm going to show you these again, just so that you can kind of refer to this. What did we say about oxygen's charge before? We said it had to gain 2 more electrons so that it would be an awful lot like neon, which is the noble gas and it's stable. So if it's gaining 2 more electrons, what does that mean that the charge on oxygen is? Oh, well, if it's 2 more electrons, it should be negative, and it should be -2. Let's double check that back with the other page. Yep, it is. What about something like lithium? It's just got 1 electron out there. It just wants to lose it. That's the easiest way to do it. So if it loses it, then it's lost an electron, so that's making it positive. And since it's lost 1 electron, it should be +1. Yep, that it is. So if this is confusing for you, what I would do is stare at this page and then go back and forth to the other slide, or sorry, to the seconds before, and just practice this a little bit, just a little bit. We will definitely practice it more in class. Okay, so with that, I'm leaving you with 2 questions. So I purposely didn't show you one where you would have to predict the charge on carbon and tin. But go ahead, try and predict the charge. It's a little tricky, but you might also notice where those rules seem to apply and where they didn't apply as well. The other thing to be aware of is that what if there was a non-net rule instead of an octet rule? So if there was 9 valence electrons actually fill an outer shell, what would the charge on chlorine be? What would the charge on calcium be? How would this change what the periodic table looks like? I would keep all of those questions in mind, but at the very least, we want you to try out that first question. Definitely think about that second question. All right, that's all for me, and I hope you all have an amazing weekend.